Hey guys, it's Vince. Today in this video we are going to be discussing a topic that comes up at least 5 times a week. I feel like I'm covering it even more than that, and that is using a stepper or a servo for whatever application you want to automate. Now, I've done previous videos on this, and I was really looking to see if there was a video done that would really cover all the details in real-world applicational use where each motor is going to be tested to do the same exact job on the same exact machine and see what result actually comes of it. And to see what major differences, if any, are present. Because, again, I think there's a lot of myths online, and I'm big into spreading the truth. I see a lot of channels that guys just talk and talk and talk, and what they're really doing is just reiterating what they've heard someone else say, whether it be on a forum or another YouTube channel. And I get asked all the time, you can sell any motor you'd like. Why are you always selling steppers? Well, I hope that this video will actually cover and really give you a breakdown of why I sell steppers. That being said, if you guys don't have time to watch the video to the end, I highly recommend you come back to this, because this is going to be a longer video due to the details involved. I feel that it is necessary to cover all these details, because if you're serious about learning this stuff and you're serious about where you're going to invest your money, it makes sense to go over these details, because then when you get whichever motor you plan on buying, you understand the caveats of each, and you understand why you've invested and what to expect as you're working with them. Okay, because knowledge is power. We really have to invest the time to learn this stuff if we plan on being good at what we do with CNC robotics. So what you have here, just to give you a quick breakdown, is we've got Microsoft Word open. I've got some timelines that I have set for the videos just to peruse through them as fast as possible. I'm trying to keep the video short, but again, practically it's almost impossible to do just to the amount of knowledge we're going to be covering. But again, the channel that I actually found these videos on is called Cloud42. It's a very good channel. The YouTube is well spoken. He's basically doing a test example of, I'm just going to break down the scene here, a test example of what he's doing for his lathe. This is basically going to reflect the RPM on this side. This is displaying the threads he'll be doing per inch for the lathe. He's using a stepper motor here. He's using a Chinese drive here, because guys always say, Vin, all you do is talk about Gecko drives. Well, I like this video even better because it's unbiased. We're talking about a Chinese drive here. Here is a board that he's fabricating. He's got the breadboard here. He's got it all hooked up and mocked up so he can test what's happening. This is an encoder which naturally is going to rotate, and as it rotates, it controls the motor's rotation. Okay, so what we've got now, just to cover exactly what stepper we're working with and what I've got here actually written: stepper motor loses torque at high speed, which actually creates step loss as torque production is reduced to the point the motor can no longer automate the load it's under. This stepper motor that he has illustrated, as I'm going to play the video, produces 566 inches of torque. That's 35.37 inch-pounds out there, and 4 Newton meters. Again, why is this pertinent? As we go through, you'll understand. Overall, though, what we have here is the actual demonstration he's going to go through. And what I want to do here is I'm going to stop the video again at 12:44, and then we'll go to these other markers and discuss exactly where we're at and what was actually covered. Okay, so we're going to go 12:44.
Now, for the stepper motor, I have this set up right now so that it's designed to be geared 1-to-1 to the lathe, and that's because stepper motors do not do well at high speeds. As the speed of the motor increases, the torque decreases, and you run a much higher risk of losing steps. And so,
okay guys, what he said there is absolutely correct. Stepper motors are not designed to be high RPM motors and produce large amounts of torque. It's just the opposite. They produce large amounts of torque at lower RPM, and as they accelerate, they lose torque. If you out-accelerate a stepper motor, it will no longer be able to produce torque enough typically to automate the load it's under, at which case it will miss steps. That's called exceeding the operational envelope of the motor. No different than if you do that in your car if you decided to just step on the gas, you watch your tachometer pin, you'll blow your engine over time. It's the same principle. I mean, every motor has its operational limits, and that's exactly what we're looking at here. Knowing these operational limits, which again, there is no way to do actual real-world testing of these operational limits until this motor is attached to your chassis. And many guys say, well, I'll just read a stepper motor torque chart and it'll tell me exactly where I'm looking for my chassis. No, it will not, because it doesn't know the gearing you're using. You have to use the exact components that torque chart was created. Otherwise, the torque spec sheet means nothing. So again, knowing the details is critical. If you ever exceed the operational envelope of a stepper motor, you will miss steps. The second way a stepper motor will have problems is if the controller or electronics that's controlling it is built improperly, and we have 98% of the time what's known as EMI penetration, where the signals that are going to the motor are being corrupt. If that happens due to outside EMF, you are SOL. You will once again miss steps. If you stay within the operational limit and the system is built properly, that is actually going to support the motor and protect those signals at all costs, you will have a stable system. Okay? Just remember that. Those two variables are the ones to pay attention to. Okay, so now we're going to run up. I'm just going to go over here again. We're at a 566 inch stepper. We're going to start now at 1244. Once again, we'll stop the video. We'll let him continue.
You typically want to run these slower. So I'm thinking 1-to-1 is about what I want. That'll give me 4 Newton meters of torque. I don't actually know if that's going to be enough, but if I try to run the stepper faster and gear it down or use a belt drive to slow it down, then we're very rapidly going to run into situations where I'm asking the stepper to go faster than it reliably can go. So if I set this to 8 threads per inch, you can see that it's going quite a bit faster than the spindle encoder is. And in fact, I can flick it hard enough. I think I can make this miss some steps. Let's see.
Okay. Just to set up the scene again, he's going to flick this encoder to out-accelerate the motor to where you're going to have signals that are going to the drive and going to the motor, or actually coming from the drive going to the motor, where they're happening too fast. And once that all happens, you get that corruption where, once again, we're out-accelerating where those step and direction signals are actually out-accelerating with the encoder, and guess what? He misses steps. Okay, the motor can only accelerate so fast. As it accelerates so fast, that is the variable at which, again, many guys encounter. And unfortunately, when they encounter it with their real system, not on the bench, but on their system, they out-accelerate. Typically, guys that don't understand why it happened will blame components. And I don't understand it because they don't do the research. But that's why you guys are watching this video. As long as we stay within our operational envelope, you will not miss steps. So you're going to watch him do this right now.
See if I can do that. There we go. I can make it lose sync and miss steps. Now you can see over here on the RPM gauge that I'm getting it over 1,000 RPM and doing it almost instantaneously. So that's unrealistic. It is never going to pop up that fast.
Okay, so we've already seen him actually flick the encoder, and it had to accelerate over 1,000 RPM in under a second to have the motor miss steps. Now, this is a Chinese drive, guys. Okay, that's pretty impressive to think that that motor can handle speeds at that rate with even holding even close to true where it's actually still rotating. Now, keep in mind also, it would, of course, have absolutely no torque at that speed. But he's just playing with it on a table like you see many YouTubers do. And once again, he's going over his proof of concept. That's fine. That's fine. It's when guys that look at this and take this in literal terms and say, oh, wow, I can get a stepper up to 1,100 or just under 1,100 RPM and use it. That's where the problem is. And once again, that's why I'm clarifying. What he's doing makes sense to test his theory. What isn't being expressed is This is not real world practical use. He said it's specific for his knowledge and for his chassis as far as the lathe he's using on. He said, I'll never accelerate to that. And again, doing 8 threads per inch, my guys out there with lathes know at 1,000 RPM, that'd be insane. And that's exactly what he covers. I'm just going to double check my stop point is at 1307. I believe he already covered this. Let's just see where we're at. Yeah, I passed it, so I'm just going to cover it real brief. He explains this is unrealistic for the application he's intending to use the motor for on his lathe, as it would never be cutting threads at this speed. And then I said watch from 1335 to 1406 mark as he explains he doesn't know if the stepper is going to lose steps for his application. So we'll go up to 1335 and we'll cover it together.
I think for some reasonable speeds, this is going to work. I think it's going to be enough. I mean, there's no way we're going to be threading at 8 threads per inch at over 1,000 RPM. It would be terrifying. Obviously, we'll have to have some protections in software to keep it inside of bounds and to do something reasonable if the operator does something unreasonable.
Now, what he just said there, that sentence is a beautiful sentence. He sets the software up to make sure that if the operator does something unreasonable, that limits are set so that it keeps things reasonable. Well, many times that is the issue. Once again, end users need to understand the limitations of what they're working with. Okay? If you don't set soft limits, if you're using, motor tuning settings that are far above what the chassis you're working with can achieve, that's the issue you run into. If you're able to move, and a lot of guys will say, I can jog the chassis, at 600 IPM, that's fine. 600 inches a minute. If it's been proven tested, not one time, not 2 times, but I would go for at least an hour at that speed to see if you got any amount of stability at that speed holding your actual trueness of the system. When I say trueness, I mean accuracy. Because, again, speed means nothing without accuracy. Okay, so knowing that and understanding those details, that plays the biggest role. It's not just about speed. We could care less about speed when it comes to manufacturing if the accuracy isn't there, because then we're producing blems, and blems are just a real fine way of saying that you're producing parts that are garbage because they're out of tolerance or they're out of measurement and you're screwed. Okay. Again, I'm just going to clarify 8 threads per inch at 1,000 RPM is in his own words, it would be terrifying. I totally agree. He also explains the software must be set properly with limits to prevent the end user from doing something unreasonable, which could lead to missteps. And it would. It would definitively lead to missteps. At 1445, we're going to go to, he introduces the closed loop stepper, and it's known as a servo. Okay, a lot of guys are calling these, or I should say a lot of vendors are calling them, hybrid servos, this, that, and the other thing. All it is a stepper with an encoder on it. Okay, so here we're going to go up to 1445, and we'll start from there. Ooh, right back here. Let's see what we got.
This is a NEMA 23 servo motor. Now, the difference between a servo motor and a stepper motor, in this case, is a couple of differences. The most important one is that it has an encoder here on the back. So instead of just one cable going to the driver, we actually have 2. And this second cable is hooked to an encoder that's on a second shaft on the back of the motor. I'm not going to take this apart because I don't want to damage it. These are not particularly expensive for what they are. The motor has the encoder on the back, and then the driver has an encoder input. And this has a 32-bit DSP, probably not unlike the one on my dev board down here. And in addition to driving the motor in this...
Okay, just to clarify, okay? The first thing to realize is that a servo has 2 cables required per motor, is the increase in cost, as both the encoder cable and the motor cable must be double shielded to prevent EMI penetration. Now, many of you guys who are building your own system and budget is everything, I'm telling you right now, when you look at this video and we look at it together, you can see how short, I'll just come back a second just so we can see it. These cables on this motor with the encoder are very short. Okay, so unless you're building this to where the motor is going to be essentially right on top of the controller, maybe a couple feet, you are going to require 2 cables, whether you build them, whether you buy them, whatever it may be, that are double shielded to once again prevent EMI penetration. Now, the theory that these motors are supernatural, it's all BS, okay? They're not the holy grail of, accuracy in terms of them being just completely invulnerable to missing steps. You guys are going to find that out. The big thing here is always to take into account your budget. And when I tell guys that if you have an encoder and you have a motor, not only, and I've covered it here, this increases costs, especially when factoring in the length required for each axis of your system that must be built. This now also increases cost of your electrical chassis fabrication, as 2 holes must be provided to support each system axis. Now, if you're building it yourself, I get guys that say, well, it's not going to cost me anything because I'm building it myself. You're wrong. It's costing you time. And I don't know what you quantify your time with. I quantify it with money. I don't care if I'm doing it myself. I don't care if I'm paying Joe Blow to do it. The fact of the matter is, if you're doing this as extra labor, quantifies to extra cost in one capacity or another. And then on top of that, you have dual cables that now have to actually be associated with each axis. Now, then after you factor all that in and you factor in now, okay, I've got 2 actual connectors I have to use, and on top of that, all this stuff has to fit in the electronics enclosure, all of a sudden, usually you find a larger electronic enclosure is then usually required to be used to support the additional space requirements for the system. Why? Because you're bundling everything else in the system. There's a lot more going on, a lot more moving parts. And again, if you're building the cables yourself, a lot more assembly time. Keep that in mind always. Okay. 1530 to 1550, he discusses the servo is immune to missteps, at least to the point that it loses steps without it knowing that it loses steps. And you'll see that exactly what we're talking about. So we'll go 1530 to 1550 right up here.
Being the motor, in this case a 3-phase motor with UV and W wires. In addition to driving the motor to the correct position, it's also monitoring the encoder so that it knows what position the motor is in. And it is immune essentially from losing steps, at least losing steps without knowing that it's lost steps.
Okay. That's an interesting sentence again that he said. It's immune to losing steps, at least to the point that it knows that it lost steps. Steppers don't know when they lose steps. The person knows. And you know how you know is when you're looking at your chassis or you're taking a measurement on a finished part and you say, oh, I missed steps. Most guys will not miss steps at the degree at which he went through and did. This is why setup of your chassis has to be done in a methodical, actual fashion. You have to understand, once again, what we're working with at an engineering level so that you understand what actual performance you can get out of whatever chassis you're using, whether it be a Shapico or whether it be, your high-end machine that you're building using Highwind KK60 rails. Whatever it may be, that is what you need to understand. The difference here is when these statements that are floating all over the internet that servos never miss steps. Well, we're going to find out with that right now. We'll go up to, we'll let it go.
So this is programmable. There's an RS-232 port on the end, and you can, I think, actually set these up so that it gets position data over RS-232. But I'm just using it to program it. You'll note there's a couple of dip switches here, but there's no dip switches for micro-stepping. So what I've done is I've already connected this, and I've set this up to be in 1,000 steps per revolution mode. So the encoder actually has 1,000 lines, which means it can count 4,000 positions per revolution.
Now this is something that's also brought up, is the resolution of the motor as far as servos having such high resolution. A lot of stepper drives now are going up to 512. Which again, we're looking in 100,000 steps per revolution if that's required. Many systems do not require that. Raptors now, I believe, are 52,000, which again, steps per revolution. And all that means to my novice guys out there is in order for one rotation of the shaft to be completed, you would have that split into roughly 52,000 plus little bits to complete one rotation. And you think in terms of accuracy of that, that's absolutely ridiculous, okay? And where the real accuracy comes from is not just from that, which is something that always comes up. It's really going to come from the combination of the motor with a drive that is capable of that, along with the transmission selected. Okay, using a ball screw transmission, a precision ball screw transmission, you're going to get the highest resolution you could possibly get. Rack and pinion and belt drive, they'll be less to a degree depending upon, again, what components you're using. But remember, and please remember this all the time, the components you select to use as a system are synergistic. There is no one component works better in terms of just using that individual component. If he doesn't have all of these components hooked up, the motor, the drive, that little tachometer, and all the neat little things going on the breadboard, this is nothing. It's a paperweight, because you need each component to do its job in order to produce the actual automation that he's looking to achieve. So always keep that in mind. There's no such thing as having a weak link, and a lot of guys like to portray that, but it's just not possible to get what you're looking for out of your system. Every component must work and play well with each other, and again, if you cut corners somewhere, expect to see it. You will definitively see it. Again, if he was to put this on a belt drive system and then go to a mill, let's say, and put this motor on an actual ball screw transmission, he's going to see a difference. There's no doubt in my mind. So again, nothing is to be taken for granted and thought, oh, well, I'm just changing the motor. And I hear a lot of guys say that, I'm changing the drive. It's not possible. Any effect you do, as far as how it affects the unit as a whole, it always will. So just keep that in mind. Okay. One other thing I want to point out, the Servo's torque rating he's using is 283 ounce-inches. And just to clarify, the stepper he's using is 566 ounce-inches. And he's going to cover why that is, but I just want to point that out real quick. We're looking at a difference of 17.68 inch-pounds of torque, and it's rated at 2 Newton-meters of torque for the Servo. So again, just want to clarify that. I'll let him continue because he's doing a hell of a job explaining everything.
But I don't need that kind of resolution because I'm actually going to use a belt drive to the lead screw with this and step it down 3-to-1, so I don't need that kind of resolution for sure. So I set this to 1,000 steps per revolution, and then we'll need to multiply the number of pulses we send to it by 3 because it's going to be geared down 3-to-1 as well. Let me get this hooked up. This works exactly the same way as the stepper driver. We've got the pulse, direction, and enable lines, just like on the stepper driver. This one also has an alarm, the signal that comes back. I don't have that hooked up yet, but I think we can get this thing into an alarm condition. I can show you what happens when that occurs. Let me hook this up. Okay, I've got the servo all hooked up to the driver. I've got the power connected to the 3 leads for the 3-phase motor connected to the 3 outputs here. I've got the power connected to the power supply, and I have the encoder connected back to the encoder. Now the connections to the microcontroller are exactly what we talked about before. We've just got the same FET switch driving the same kind of optical input in the driver, and this should all be working. Yep. There are a few differences between the servo and the stepper motor, and one, of course, is the encoder. This is a closed-loop system that cannot lose steps, or at least if it...
Once again, and I'm going to just come back because I want you to hear it for him to say it. That is not true. So listen closely.
The servo and the stepper motor, and one, of course, is the encoder. This is a closed-loop system that cannot lose steps. Or at least if it does lose steps, the driver will know about it and will raise the alarm and stop the motor.
Okay, that's about it, guys. Now you heard the truth. If it does lose steps, which you will see, it will trigger the alarm and it will stop the motor. Okay, so when guys say, well, what's this huge difference between a servo and a stepper, you're about to see what the huge difference is, and he's covering it real well.
And so we don't have to worry about that. The other big difference here is that for the same size motor, this thing produces less torque than the stepper. This stepper motor produces about 4 Newton-meters of torque. This servo is only 2 Newton-meters of torque. But what it loses in torque, it makes up for in speed. This thing can run a lot faster while retaining its torque curve than the stepper motor ever can.
Now, Think about what he just said. This is faster, but has less than half the torque of a stepper. If we're doing machining applications, in order to get the same torque out of this, you have to do the gearing like he's talking about. Otherwise, you're better off going with the stepper. It's a simpler system. It's got less parts. And once again, we look overall at cost. You're not building 2 cables. We're not doing all this, but we'll get into that. It's just interesting to hear that this motor is faster, which it is, but it also produces under half the torque of a stepper. And we're using this, and this I cannot say enough, we're explicitly using this motor, either motor, for the application of lathes, and using a lathe to actually do threading. So when we think in terms like that, and when we go to real world use, once again on the machine, you'll see how much of this is just theory and talk, and how much of it is noticeable. Because that's what we all pay for, is, am I going to see a difference, or is this just talk on the table? Because to me, that's what I look at. If you tell me that I'm going to get 600 horsepower somewhere, like most guys, we're interested. If it's going to the rear wheels. If you're telling me it's doing it to crank, that doesn't impress me. Okay? That is something you're going to feel in the seat of your pants, so to speak, and that's the reality of what you should all be looking at, because that's what you're paying for. That is really what you're paying for. So again, I'm going to hit play here.
So what that means is we can run this faster and gear it down. So I've ordered the right pulleys to gear this down 3-to-1 to the lead screw. I think that's probably going to be about right. And that's how I have the software in the microcontroller configured right now, assuming it's going to be 3-to-1. But I also ordered the right belts for 2-to-1, and we can try them both and see what the trade-offs are. And it all comes down to a trade-off between speed and torque. So if I go 2-to-1, I get a higher top speed. If I go 3-to-1, I get more torque. And we need to get it on the machine, actually open and close the half nut, take some cuts, and find out what's going to be actually needed. So if I put this in threading mode and put it down to 12 threads per inch, if we were running the stepper motor 1-to-1, you would turn the lead screw once and get 1 revolution on the stepper. With the servo, it should go around 3 times because I've changed that ratio. 1, 2, 3. Yep, so that's working. So as a result then, when I flick this, you can see that that motor is going quite a lot faster. And moving itself around the table, but it's not having any trouble with the lost steps. Now if I flick this hard enough, I can make it lose steps, but instead of just losing steps and continuing to run, the driver is actually going to kill it. Now keep in mind, this is running 3 times the speed of that stepper.
Once again, let's clarify everything. It's running 3 times the speed of the stepper at less than half the torque. And we're using this, once again, for a machining application. If you think in terms like that, most of my guys out there are going, well, I'd rather have the torque because that's more usable for this application. And I would agree with you myself. Let's play it.
There, and I finally...
Okay, let's look at when this thing actually, because this is cool that we've got the RPM here. Let's look at this and see when it actually misses steps. Okay.
Can make it lose steps, but instead of just losing steps and continuing to run, the driver is actually going to kill it. Now keep in mind, this is running 3 times the speed of that stepper.
See that RPM again, see if I can catch it. Okay, he's at about, let's say 600 right there. Okay, he was about 800 RPM. He never broke 1,000, and the motor missed steps. Yet the stepper went over 1,000 at that speed to miss a step. And we've seen that.
There.
You'll see it right there.
Got it to actually freeze.
Okay.
Now what's happened, I don't know if you can see it, but there's an LED flashing right down here on the driver. And that's the alarm LED telling me that the driver has lost sync with the motor. And that's just because the error in position between where the driver was trying to drive it to and where the motor actually was greater than a threshold. That's all configurable, and that's something that we may need to tune.
Okay. Now, what he just said there, it's all configurable, and it's something that we may need to tune. Well, technically speaking, to be fair, That's the same thing we could say about a stepper, because in Mach 3 we do motor tuning, and once again that's what we're trying to do, is find the operational threshold to the application we're using. So what did we just learn in real time? So far we've learned that both motors will lose steps. The difference that we really identified is that one driver will tell you with an LED, oh hey, I missed steps, and stop, whereas a stepper will not do that. Now, most guys out there are going to say, okay, so let's fix this. I mean, realistically speaking, if I test my machine and I set it up properly with a stepper using whatever motion control software I want, and I do the proper calibration testing, I'll know the operational envelope because I'm checking my accuracy as I should with the proper dial indicator, preferably with 1 to 5/10,000ths of an inch, and then we set our acceleration based on those measurements to make sure that we stay well within them so we know our operational envelope. Right? That's logic, right, guys? Or we say, I want to buy a servo to tell us that now we've missed steps and it stops, and it gives us a fault LED. That's your option. But guess what? You're still going to set that servo, just as he said, with the same software to do the same thing in order to, once again, stay within its operational envelope. There is no supernatural motor. You just saw the truth. But it gets better because I want to see this on the machine like you do and see what the difference is. I want to see in real world time, where is this major difference that we're talking about. Okay, so I'm just coming back to my notes here. Again, this was the part that he discussed. The servo's immune. The servo's torque rating is 283 ounces. We know that we're basically getting double the torque usable using a stepper. The servo would cost more based on matching the stepper's rating torque. The servo is faster than a stepper and loses torque less. Considering the stepper he chose has over double the torque available to work with, you're essentially creating a wash when comparing the two motors, in that as the stepper motor goes faster, your torque will reduce, but it will still offer plenty of torque available until it reaches the edge of its envelope at higher speed, where the servo will hold its torque at faster RPM until it exceeds its operational envelope, in which case the torque it produces will be so low the motor will miss steps as it no longer is able to handle the load of its application. So guess what we just determined? Both of those motors will eventually bleed off and do eventually the same thing. The difference is that if a stepper has more torque, because this is kind of hard to do with a motor that's not equivalent, okay? But let's think in terms of what we're working with. If a stepper motor has more torque, in this particular case, roughly over double, then as we accelerate that stepper, we actually have a buffer there because we only need so much torque available to automate the load that it's been applied to. So you can keep accelerating that and offset that using a motor with larger torque output. Now you can also translate that torque, being we know we can't get speed, into different gear ratios. And if we do that, we can increase speed if required, and if, again, we have the proper torque ratio so that we can automate the load we're trying to do. This is fact. This is done in vehicles all the time. Okay, they're just not using a stepper motor. Okay, so realistically speaking, what we just learned is both motors basically behave the same if they are exceeding their operational envelope. There is no supernatural motor. What we did know is that one will perform better in certain aspects than another under certain aspects, but they can both perform very, very similar if we even the playing field, so to speak. And we're going to see that when he goes with the actual system setup he has. Because again, we're using both motor in the same sequence to do real-world testing. So at 1935-2028, he discusses losing steps with the servo. He then explains the motor is running 3 times the speed of the stepper. And again, I already pointed this out, but forgets to reiterate at less than half the usable torque, which again, for machining, it's critical to have the torque. It really is. He then shows the servo missed steps where the driver then kills the motor. Now we're going to come over to the second video where we see them live. And this is something I hope you guys stay tuned for, because I'm telling you right now, this is a thing of beauty to see what we're about to see. It's a little longer. We're going to watch from 3:10 to 15:57. I've already got the video pulled up, so I hope you guys have some popcorn. And we're going to try.
You'll remember from the previous video a NEMA 24 stepper and a NEMA 23 servo motor. What I have mounted on the lathe right now is the NEMA 24 stepper motor, and I've got two 48 tooth pulleys One 3D printed because I ordered the wrong bore size and the replacements are not here.
I'm actually going to let him start from here, even though I said 310, I believe. We'll let him start from here because I love the way he explains everything.
Yeah.
Once again, he's real
and
thorough.
The other is a proper aluminum 3M pulley, high torque drive pulley directly on the motor shaft. So this is geared 1-to-1. Then there's also a gearbox in the lathe, and it's set up also for 1-to-1. It's possible one of these is, I think, a 4-to-3, or maybe it's a 5-to-6 ratio, either increasing or decreasing, and the other one is a 2-to-1 or a 1-to-2. So you can switch this to a mode that'll double. I think C doubles, and it cuts the speed in half. So we have some other options we can use for gearing, but for now I've just got it set 1-to-1 all the way through. I've also made some marks on the pulleys, so maybe you can see this in the video. There's a mark here on the shaft going into the lead screw, and I've got a mark up here on the pulley that's coming off of the spindle.
One other key point I want to discuss, because a lot of guys that watch videos like this tend to forget. Once again, he's already done the mock-up on the bench, and if we look at the motor setup he has here, he's still using the same braided wires here. Nothing is really finalized in the sense that the electronics you're going to find is not in the enclosure properly. Nothing is done using the shielded cable and the grounding and all that stuff that should still be done, even though in this particular instance, he is not using this for, so to speak, CNC use. He's not using a computer in any way or capacity other than the low voltage electronics that he's using to control the signal manipulation. Now, I just said low voltage electronics. So should shielded cable still be used? Of course. Mainly because I'm sure a guy this detailed, and I'm just telling you as you watch his videos, he's very detailed, he's very well spoken. Somebody going through this level of detail, he doesn't want mistakes with what he's doing, nor do many of you. So again, it's not an option. I have guys that feel it's an option to do this. And what they end up doing is, and you've seen many YouTube videos, many of you guys have already pointed them out to me, where a guy builds the system and then goes back and rebuilds the system, which to me it makes absolutely no sense. You're better off saving and doing it right the first time. But looking at this, I want to reiterate, this is still what I consider mock-up phase. We are not yet done because, again, he's testing his theory. He's still testing everything on the machine. When everything is said and done, this should be assembled properly. This should not be run like this for 6 months until he decides to get around, like many guys do, and then they find that, oh, hey, it was working great when I first did it, and then they say, oh, well, this is a POS because basically I've built it, it worked for a week or two, and now I can't understand why I'm having problems. Well, why you're having problems is you didn't go back and build the controller properly. This is fine for experimental use. After the experiments have been tested, all variables have been corrected, it's time to go back and build the controller properly. And if you don't believe me on that, you look at a car that's in a showroom. It didn't end up in the showroom. It ended up in pieces at a track until they test everything out. Everything gets functional. And then once they make sure at every engineering level everything is cooperating and working as it should, then they do final assembly, put the beautiful paint on it, and there you go. This is the same concept. You have to look at this as what he's doing. Do not take this literally. I'm sure he never intended that. He's expecting you guys to look at this, like many YouTubers that I feel implement that, and take this, learn from it, but also understand that it's in an unfinished process. So many guys forget this is not done and think, oh, I'm good. And then they run into hiccups, and then they blame their components, where once again, it's not the components. It's lack of knowledge from the end user. So again, keep that in mind.
So that you can see how those are turning. Now, unfortunately, this pulley is not turning 1-to-1 with the spindle. It's actually turning slower, and then there's a multiplication with the belt. So the encoder is running the same speed as the spindle, but this pulley is not necessarily. But you can at least see that they're turning. So let's set up some basic cuts and see what we can do. Got this set to 5 thousandths per revolution, and I've got a piece of material in here. This is 3/4 inch 1018 mild steel.
And just to clarify again, he's using the stepper motor right now to do the testing at this phase.
And let's just take some cuts on it and turn this down maybe to 1/2 inch so we can try to cut a 1/2 inch thread on it. find my 0 here, going nice and slow. Okay, and let's just start by taking 10 thousandths. We don't want to overwhelm the stepper with the feed, and I don't really know what it's going to do. Let me bring the speed up here. That's about 1200 RPM.
98% of engineering is trial and error, guys. 98%. Because theory goes right out the window until this motor is mounted to the machine. Just no different as when you'll mount your motors to your machine. Don't go by specs. Don't go by what Joe Blow said his machine can do. Start slow like he is, and then you build upon that. The only thing I wish he was doing right now is writing this down. Every test you guys do, learn to document. I had somebody once message me, and I found it interesting. He said, you're very methodical in what you do. Well, that's engineering. You know, if I'm not methodical, I'm chasing my tail. Many guys will contact me and say the same thing redundantly, and they're essentially practicing the definition of insanity because they're not documenting what they're actually trying and what they've learned from that. Because remember, even if you learn what doesn't work, you know what doesn't work. In this case, he's starting low. He builds up. That's common sense. He's going to start at a low, an actual low cut rate, and he'll go higher and see exactly what is determined. Like he said, he doesn't know how the stepper is going to behave. So let's see what happens.
Let's just take a cut. That seems to be handling that just fine. Let me bump this up to 7 thou per revolution, and let's take maybe 15 thou depth of cut.
All right, so we already increased 5 thousandths on top of that. We're at 15,000 depth of cut. Like butter.
Okay, that was easy. Let's take another 15 and let's go faster.
Okay. Now, what I just said to you, I'm giving you the holy grail of trial and error engineering. As he made an adjustment, he first did the 10,000 depth of cut, then he went to 15,000 depth of cut. Then the other variable he introduced was RPM. That should have been documented. Why do we document all those steps? Because we want to know how they all work well together. If we document it, we then can go back and review that and say, oh, well, look at this. When I increased RPM to such and such, this is the result that actually I got. Many end users do not look at the patterns that are associated with a robot. The robot does what you tell it to do. If it's set properly, it's going to produce the same pattern over and over again, pending the variables are all checked off. Many of you forget that's something that is a necessity. The guys that get that, the guys that really fine-tune themselves to think how the machine reacts, they're the best machinists. That's secret tip of the day. You can write that one down. I hope you are, because it's a fact. Document every variable. The better you get at those variables, that's what's going to determine what kind of products you produce.
Okay, so far so good. It's just behaving like a lathe, which is exactly what I want. And I'm going to target 1/2 inch for this. And we've still got a ways to go. I'm still well over 650. Let's try taking something a little deeper. Let's take 20 thou depth of cut. And again, I'm going 7 thou per revolution.
Okay, so even if he was to document this right now, super easy to do. I get guys that say, I don't want to write all that. Document with your phone if you want to do it that way. We've got all these high-dollar phones. We've got all this technology. And, you know, we got to start using this stuff the way it was really intended to really make our lives easier. And this is something that you guys are going to learn from. So, again, he's probably taken his own mental notes. I don't know. We don't know how many times he shot this video, if this was just a one-over or whatnot. But in true engineering terms, if you really want to learn something as you're building something like this, document every variable that you're testing, because you will learn so much.
let's take 25 and let's bump it up to 8 thou.
Okay, now we're at 25 thousandths, and he's going to the 8 thou on how he's actually cutting. This is still amazing, and he will confirm that. We're doing this again with that stepper motor. You can also see the finish it's producing.
And of course my compressor just kicked on. Okay, we need to take off about another 75. So let's take that'd be 40. Let's take off 50. And yeah, I'm really pleased with this. That's a pretty good feed rate. And let me go ahead and bump this back down since we'll go ahead and take one more roughing cut. Then we'll dial this back down to 3 thousandths per revolution for a finished cut, and we'll take half of what's left. It looks like we've got 24, so we can take 12. Actually, that'll take us right to size because this is double. Okay, so we need to take 24, so take 12, so I'll take 6 on the dial. And this should be half of what's left. Now I'll go ahead and run this even a little bit faster. 3 thou per rev finish cut. And that should put us right at half an inch. And what do you know? It's right at half an inch. Okay, let's do some threading. Half 13, anyone? Bring a carbide threading tool here.
So I would say for most end users out there that are looking at a similar application, whether it be for a lathe or mill, you can see that steel he's working with. Once again, I'm sure that what he's doing now, again, and I reiterate this, it's testing. So if there was a problem, these are not finished parts that would cost him money. These are just to go through and make sure that the proof of concept is there.
And let's start by making a gutter to run off into, and we do not have to run it that fast for that. That should be plenty. Now let me just get my zero here. Now, if you haven't noticed, I'm not, being super careful with this. Let's switch over to thread mode and go to 13 threads per inch because I have a half 13 nut here that we can use to test.
So this is the real test, guys. This is what he's done with this system. That's the true application he's looking to do, is to do threading. And again, we're going to see if the stepper can handle it.
Set 0 on the press style. I've already got 0 on the compound. Let's take 2 thou just as a scratch pass. So far, this servo is performing well.
Let me just clarify. This is the stepper. This is not the servo. I think he just forgot for a second what he was saying.
Let's check that. Make sure that looks right. That looks right to me. Okay, let's take, not on that dial. Let's take another 5 and see what that looks like. Speed it up a little bit. actually, I wasn't paying attention to which number I started on, so we probably are going to have a scratch. Funny. Pay attention to the threading dial now. Okay, that's starting on number 1. Sure enough, that's slightly out of time because I didn't pay any attention. We'll pay attention now. Let's take 8th thou now. That's nice. Let's take 10, since we're still at the beginning of the thread and it's easy. You can hear the lathe bogging down just under the load of the cut, but you can see, hopefully, that the timing is still perfect because the microcontroller is reading the spindle 4,000 counts per revolution and keeping up. Adjusting in real time. Let's go a little faster. Let's actually take a cut this time. Take 5 here. Another 5. Another 5. And another 5, and I'll wait for my number to come around here. And there we are. Oh, there's almost no rock. I hit it exactly right. Accidentally. Wow. That looks really good. I'm really pleased with that. Gonna try something finer? I'll try quarter 28. Hey, let's try quarter 28.
I think many of you would agree that that came out excellent. I mean, again, as we go longer into this video, you're going to definitely see what many of you may or may not be aware of, that you're not going to see a difference.
Switch back to feed. Okay, here's a piece of mystery metal, some kind of steel. You just stick it out the same amount so that my focus will be close. Let's start by turning this down. Okay, that puts us 3 under, it'll be fine. Okay, and let's switch over and thread 28 threads per inch. So switch to threading and go to 28. Okay, we'll call that 0. Okay, we'll take a 2 thou scratch pass. looks good. Okay, let's take a little bit here and see how it looks. Five more. Okay, I'm not sure what this material is, but it does not like to cut. Okay, well, I think that is to size. Quarter 28 nut. And there you go. Beautiful. Okay, well, I am very, very pleased. I'm not pleased with this material. It was hard to cut. I think it's stainless.
He thinks it's stainless, and we just did that with the stepper.
Mystery metal that came out of a junk bin at work, I think. So that worked really well. Motor's just a little warm, similar to what I would expect if I were running it on the mill. I'm actually really surprised. I was expecting, after all the comments and after all the discussion, to have a lot of trouble with this motor running 1-to-1, but so far that looks good. Can I stop it? Is there a limit? Yeah, absolutely. But this is really, for all practical purposes, the kind of thing I do. We just cut.
And just like he said, for all practical purposes, like many of you, that is what you would experience if, once again, we stay within the operational envelope of the machine. I cannot emphasize that enough. And when I say of the machine, you didn't hear me say of the motor, I said of the machine, because the motor's operational envelope will always be dictated by the machine, and all variables when connected to the transmission, and everything is incorporated. It's not when it's on the table, like so many guys like to portray and say, oh, look at my machine run. That means nothing. This means something. And when it holds that level of accuracy, and especially considering, let's not forget, he's got a microcontroller that, again, I don't know what kind of circuit board he's using there or whatnot. It looks similar to an Arduino, whatever it may be. It's not true CNC. It still has robotics in it because, again, that's doing all the processing for him to get those threads correct. But when you think about it like that, it's pretty amazing that all, like he said, of the peanut gallery, so to speak, from forums and messages and everything else, they, belittle stepper motors so much. When we look at the machines and we look at what's produced with them, it's hard to argue that. And that was, again, reiterating, he believes that was stainless steel it was cutting. And again, I myself sell 600-ounce motors, so I can tell you without a doubt, when it's used properly and on the proper machine, you have a lot of cutting power, and that just definitively showed that. So now he's going to move up to, I believe, the Servo.
Half 13 threads in steel. We tried a bunch of different feeds. We were feeding fast with relatively heavy servo in here instead of the stepper, and you can see because I've got the servo, I've now switched to a 3-to-1 belt drive. So this is a 24-tooth pulley here and a 72-tooth pulley on the lead screw. Let me grab my pen and put a mark on that just so you can watch what's happening. There, can you see that? Yeah, you can see that moving. Okay. I am set right now to 5 thou per revolution feed rate. Now, ironically, the servo seems to make more noise, at least this servo seems to make more noise than that stepper with that good DSP driver. So I'm not sure exactly why that is, but the stepper did fine. Let's see how the servo does. Same drill, we'll take this piece of 3/4 inch down to a 1/2 inch.
Let's see if we can detect the differences, guys.
Start with a nice light cut, maybe 10 thou. Do this about 1,000 RPM. is just fine. Let's go right to 20 thou. And again, now we're up to about 1200 RPM. That was 20 thou per side. Let's just take 25 and just see what happens. Oh, yeah. Yeah, let's see where we are. That makes a beautiful finish. So far, servo's working great. 635. Which means we need to take another 67. Let's go ahead and take 30 and just see how that does. Oh, no problem. Okay, so the feeds are working great. Let's switch to threads. And let's go to 13 threads per inch. And let's cut a half 13 thread on this thing. So a nice wide gutter just so there will be no drama. There we are, just touching, 2 thou. That's right. Looks like I did the math right. Okay, let's take the rest of the first 10. And let's take 10 more. Go a little slower than that just so I can hit my numbers. Right in time. Let's take 10 more. Now, what you heard there is interesting. I'm running this on a 1200 RPM belt, but I'm dialing it way down with the VFD to what? 220 RPM. And so it's running very slow. So when I enter the cut with a nice heavy cut, it's slowed down quite a bit. But because I'm reading the spindle 4,000 counts per revolution, it just tracked perfectly with it. You can see there's no issue at all with the timing, even though it radically changed speeds during the cut. Okay, so it's a little faster, and we start taking 5 at a time now. Okay, we got to be there now. And oh, that is just about right. Just a tiny bit of rock in there, and that's just because I missed all the way down to the bottom. So there's another perfect half 13. Well, I'm really happy with this servo and the way it's performed. It's quite a bit smaller than the stepper because it's a NEMA 23 as opposed to a NEMA 24, which is some kind.
Now, again, guys, he's talking about NEMA 23 versus NEMA 24. My 600 ounce NEMA 24. The big difference is the length of the motor. That's how we get the extra torque out of them. Mounting pattern is the same as the NEMA 23. The beauty of that, you get more torque in the same chassis size format, other than the length of the motor, which never really interferes with much. But overall,
kind of odd size.
We'll let him continue.
It comes mostly from Chinese manufacturers, but this is running quite a bit cooler, even though it's smaller. It has less surface area to dissipate the heat, and that would make sense because the servo driver is going to run less torque through it when it doesn't need the additional current to keep it in sync. As long as it's running fine and staying in sync, it's going to run with a lower current and only peak the current when it has to keep it in sync. So I'm pretty happy with that. There's lots of tuning left to do. There's lots of tuning that can be done on the servo. We need to test the limits, see how close we really are on power.
And that could be said about the stepper as well. But realistically, in real-world testing, this is a long as hell video, but it's worth watching it to the end because now you see the truth. They essentially performed the same because both were used in this video well within the operational envelope, and therefore the result is virtual perfection. Why? Because the end result is one motor uses one method in order to find position, where another motor uses its method to find position. In the end, it's the same. I've done a video on this before. Lin Engineering has posted in their FAQ forum on that, who is one of the most pronounced actual motor distributors in the world, and it's a fact. Many guys misconstrued what the realities are of a stepper and a servo, and the biggest difference is how you apply them. They're great motors. They both work exceptionally well, but in general performance, or I should say where general performance is going to be used in milling CNC applications, especially for civilian robots, it's really hard to beat a stepper motor just for its simplicity. And again, the accuracy achieved, you saw, the end result is the same. Now, of course, if he was to exceed in either motor's capacity, the operational envelope, be it speed, where they both couldn't supply the proper amount of torque to get the job done, or if he left this setup the way he has the mock-up setup once again, and he didn't go through and do final assembly and the electronics enclosure and do everything that was supposed to be done, it is very possible that over time he may experience issues with stability. In either motor, it's not one or the other, it's either motor, because again, both are susceptible to electromagnetic interference. We don't know what else he has going on in his shop. If you check out his channel, you'll get to see what else is going on. Well, I want to say thank you all if you guys have stayed tuned to watch this whole video. It is a long video, but I feel there's a lot to be learned here, and the proof is in the pudding. When you guys get to see in real-world testing in the exact same machine, the two different motors to see what end result is produced, you saw the product that both of these produced were virtually the same. So now the question is what best suits your application? And that really is something you have to look at 98% of the time, like I said. For actual civilian-based CNC or personal CNC use, it comes down to budget, because that's going to play the biggest role. Once you begin making money with your machine, then you have more options if you want to do that. But I can tell you, many guys I've retrofitted from servos to steppers and just love them for that reason, because they're simple. You don't have to do all, most servos have extensive programming if you're doing PLC. He discusses at the end of the video that he was hoping that some of his viewers would actually recommend an AC servo, which is a little more detailed in setup. But again, you guys got a good feel for what is actually possible. And like I said, to reiterate, he's using a motor controller to do what he just did. And this is not a true CNC machine, but you did get to see what is capable of a servo and a stepper in the same capacity at the exact same load using the same type of machine, and you got to see exactly what the end result is. And to me, that's priceless, because most vendors will never show you that. They'll simply state, hey, this is better, this is better, this is better. Now you've gotten to see it, and I hope you learned some. So again, for you guys staying tuned, love you guys, all my subscribers. I hope you guys have a great new year. We've started out with a good bang, and this year be real productive. If you guys have questions, of course, message me direct, because I know watching this long a video, there's going to be questions at storm2313@gmail.com, or you can message me through my eBay store. Once again, eDealers Direct. You'll see the link on the screen. Again, I look forward to hearing from you in the comments. Please like and subscribe. Take care.